Hello, everyone. Thank you very much for joining. My name is Albert Kahira, and I'm going to be making this presentation on behalf of Nguyen, Leonardo, Takano, Rosa, and Mohamed Wahib. So our paper is an oracle for guiding large-scale model and hybrid training for convolutional neural networks. And in this presentation, I would like to first give a quick outline. I'm going to give a brief introduction of the topic. Then I'm going to talk about the strategies for distributed training of convolutional neural networks. Then I will introduce our oracle, ParaDL, which is what we use for performance projection, and then some evaluation with the experiments we did, and then I will give a summary and conclusion. So let's get to it. So looking at the recent trends in deep learning, one would notice a few key themes or a few things that have been happening. One of them is that most recently we are having very large data samples that are emerging, especially from the scientific computing society. And some of these include things like Cosmoflow that I will discuss a little bit later in the presentation. And we're also seeing the emergence of very large deep learning models, especially in natural language processing, NLP, and other domains as well. And these large models is in an attempt to build better accuracies and also apply deep learning in other fields. And because of these reasons, what we have noticed is now that deep learning is continuously being trained in HPC infrastructures. So there is a prevalence of deep learning applications in HPC infrastructures. And this is to leverage the parallelism offered by HPC. And the approaches so far have been two common approaches to do parallelism in HPC: data parallelism and model parallelism. And initially, data parallelism was, initially model parallelism was proposed, but didn't really pick up because data parallelism was quite sufficient. So data parallelism is kind of like the go-to method when you want to do deep learning in HPC. And this is because it's very easy and straightforward to implement and comes well implemented in almost all the frameworks. And the performance has been okay so far. And the models and datasets up until now have been largely manageable for data parallelism. However, data parallelism is not feasible in all cases, as we will see, and I will discuss a little bit more into the limitations of data parallelism. First of all, the main limitation of data parallelism is memory capacity. Like I mentioned earlier, data parallelism involves replicating the entire model in different GPUs and then doing an all reduce at the end of each iteration. Depending on the model size, this can become a problem because with models that have many parameters, this could go up to 350 gigabytes. And it's not possible to replicate that in every GPU because we don't even have a GPU with that much memory capacity. So, and also with 3D scientific datasets such as Cosmoflow, the data samples themselves are also really, really big. Combine that with a relatively big model, then that does not fit into the single computing element. And therefore, it's impossible to use data parallelism in these kind of scenarios. Another problem with data parallelism is communication overhead. This is mostly due to the all reduced collective that happens at the end of each iteration in the case of data parallelism. And as you moved higher with the number of GPUs, then this becomes a huge bottleneck, especially at scales of above 1000 GPUs. The other problem that has more or less been addressed, but it's still kind of an issue, is the degradation in convergence accuracy. Because data parallelism involves replicating the model and giving a different batch size to each, a different batch to each model. As you increase the number of GPUs, then you increase the mini batch size. And at a very high mini batch size, then there is some performance degradation that is observable. And because of these reasons, there has been some renewed interest in model parallelism or hybrids of model parallelism with data parallelism, as we will see later. So what's the problem with model parallelism? First of all, it's really important to understand the limitations and the scalability of large-scale model and hybrid parallelism training for convolutional neural networks. And the problem with the model parallelism currently is that there's no existing way to determine what is the right parallel strategy, because there's so many different ways of doing model parallelism, as we will see later. And because of this, there's quite a lot of time that is spent trying out different strategies to find which one works. And this strategy becomes obsolete as when you change the model architecture, or when you change from one computing system to another computing system. Therefore, the contributions of this paper are as follows. We look into those challenges of model parallelism and provide an oracle that can guide in training in selecting, or rather determining, the correct parallelism strategy. But to do that, we first of all define all the main parallelism strategies of convolutional neural networks. And then we provide a comprehensive analysis of compute, communication, and memory footprint of each of these strategies. Using that analysis, we propose an oracle that we call ParaDL that can project the ideal performance of distributed training of convolutional neural networks. And in so doing, it can guide the choice for the right strategy for a given data, model, and computing system. And this oracle can also help identify optimization opportunities or bottlenecks in a specific framework, or just bottlenecks in training convolutional neural networks in model or hybrid parallelism. We also implement all the parallelism strategies that we mentioned, and to validate our model. And finally, we show that the ParaDL can be used to expose performance and scalability trade-offs. So what are the strategies for distributed training? Well, we focus on 4 main strategies based on how we split data and model dimensions. And in this strategy, there are sub-strategies that I will talk about. So the first one, of course, is data parallelism. Data parallelism involves splitting data on the batch size. So you have different batches going to different GPUs. And then we also look into model horizontal parallelism, and this generally involves 2 things. One could be splitting the channels, or splitting the filters, as I will show in a short while. We also look into spatial parallelism, which involves splitting the data sample or the image, 3D image or 2D image, along the height, width, and depth dimensions. There's also vertical parallelism, in this case pipeline parallelism, which involves splitting the model vertically and placing each set of layers in different GPUs. Apart from that, the 4 strategies, we also look into a hybrid of 1 or 2 of these strategies. And specifically, we look into a hybrid of data and spatial parallelism for the case of CosmoFlow, and a hybrid of data and filter parallelism. So these are the graphical representations of the different parallelism strategies. Like I mentioned, data parallelism is the entire data is divided into the number of processing elements available, and then we have an all-reduce collective at the end of each iteration, right? For layer parallelism, it's a set of layers is split according to the number of processing elements available, and we can have, for example, the first 3 layers in one processing element and another set of layers in another one, etc, etc. And then we have this layer to layer, or rather this communication to pass the activations from one processing element to the next one. For the case of spatial parallelism, we specifically split along either the height, width, or depth sorry about that. And for the case of filter parallelism, we split along the filters, and for channel, we split along the channels. So having talked about the different strategies that we're going to focus on this work, let's look at the oracle itself, which we call ParaDL, and that can ideally help us in projecting the performance of this parallel strategy. So this is a quick overview of ParaDL. As you can see, ParaDL takes a dataset specification, that is the number of samples and the total dataset. It also takes a CNN model, that is the number of layers, the inputs, and the outputs and the weights, and also a computing system. So this could be any supercomputing, in our case, ABCI supercomputer. And in this, we take the architecture breakdown, which is like interconnect hierarchy, bandwidth, and the number of flops and memory capacity, etc. By taking these things, we can then project the computation time of a specific parallel strategy, the communication time, and the maximum memory per processing element. So to formulate ParaDL, we use a combination of analytical and empirical modeling. And the reason for this is because a pure analytical model is impractical because different frameworks have different optimizations. And for this reason, it's not easy to generalize on across all frameworks, and therefore we choose a hybrid of analytical and empirical modeling. Empirical modeling for functional requirements related to the parallel strategy, for example, number of processes, and in the case of, for example, filters, how many filters we can split, etc, etc. And then empirical parameterization for functions not related to the parallel strategy. So we look at, we profile things like the time for forward propagation, backward propagation, and weight update, and also communication parameters alpha and beta. So how do we do the performance and memory projection? Or how do we estimate the total training time in one epoch and the maximum amount of memory required per processing element? Well, based on the elements that I've just mentioned previously, we can calculate, for example, in the case of data parallelism, the computation time required by combining the forward pass, backward pass, and the weight update over the total number of data samples divided by the processing. And for the communication side, using the ring-based algorithm, we can get the total communication time. And the same applies for memory, where we focus on the inputs, the outputs, the weights, and the biases. So using these equations, we can estimate the total training time for each epoch. And in this case, I've just given a sample of data parallelism. But here we can see the total time for all the parallelism strategies, including the hybrid strategy I mentioned earlier of data and filter parallelism. And this table kind of gives a summary of everything and all the related strategies, also with the serial one as a benchmark of where to start with. And you can see with the serial we have no communication, and also we have the limitations in terms of the number of processing elements. So in the case of data, for example, p is less than or equal to the batch size, etc, etc. So these details are more of these details are available in our paper, and especially in the appendix part, where we discuss extensively how we arrive at these equations. So that being said, now how do we use ParaDL, or what is the purpose of ParaDL? First of all, ParaDL will help us to know the best strategy for a given CNN model, dataset, and a budget. And it will help us to identify the time and resource provision from a system. If I want to train a deep convolutional neural networks, I can know in advance how long it's going to take to train that in a specific system, given a specific set of requirements. And it will also help us detect abnormal behaviors in training convolutional neural networks and identify the limitations of parallel strategies, shortcomings of frameworks, and bottlenecks in the system. And we will discuss a little bit more on this because we used ParaDL extensively to identify some of these bottlenecks. Finally, ParaDL can be used as an educational tool for parallel strategies and to improve understanding of parallelism in deep learning, and especially convolutional neural network. So moving on to our evaluation. In this evaluation, we are just going to show selected results because it's not practical to show everything in 20 minutes. But before that, I want to mention the datasets we used. We have ResNet, the models were ResNet 50, 152, VGG16, and the CosmoFlow model. We picked these datasets and models to highlight on the different aspects in convolutional neural networks. So for example, VGG is a traditional convolutional neural network, while ResNet is a convolutional neural networks with skip connections, and CosmoFlow has the 3D convolutions that are also important to highlight. This was our evaluation environment, the ABCI supercomputer, and basically each node has 4 V100 GPUs that we use for this work. So on the results, I would like to first of all present the results of data parallelism, and we were able to attain very good results with data parallelism. And I would like to reiterate again, part of the reason why we are able to obtain really good results, it's because this is a combination of analytical and empirical model. So with data parallelism, we got accuracies of above 90% for all the three models. And one of the reasons for this also is because like I mentioned earlier, frameworks are very well optimized for data parallelism, and therefore we don't incur a lot of computational overhead trying to implement some of these strategies. For channel, this is where we see a little bit of a drop in accuracy, and we will discuss again why this is the case in the discussion section. But part of the reason for this is because to do channel parallelism, we have to do to add extra functions such as concat or split functions, and these create an overhead in the strategy. So even though we are able to get some good accuracies, it's still not as good compared to data parallelism. And for pipeline parallelism, this was quite an interesting case. We were able to achieve pretty good accuracies, and the key thing with pipeline parallelism is that to be able to achieve very good accuracies, you need all the stages of the pipeline to be able to take around the same time. And we used ParaDL to determine which was the best way to split the model in order to achieve very good accuracies. Finally, with CosmoFlow, the 3D accuracy, we also able to achieve accuracies of above 70% for most of the cases. This is the specific case where the data sample is too big to fit into a single node, and therefore we use a hybrid of a spatial and data parallelism, where we do spatial at the local at the single node, and then we do data parallelism to run across many nodes. And this is the summary of all results, basically, for all the strategies combined. I'm not going to go into the details of this, but the results are available in the paper. So let's talk now about the parallelism limitations and the bottlenecks that are clearly visible and that we are able to detect and highlight using ParaDL. The first one is communication. Communication takes many forms. For example, in the case of data parallelism, we have a gradient exchange, which takes quite some significant time, as we mentioned earlier. There's also layer-wise communication in the case of pipeline parallelism or pipeline parallelism, and peer-to-peer communication for hello exchange in the case of spatial parallelism. And we wanted to highlight on this is because one would think hello exchanges would be pretty fast because the data that is being sent is not very large, but actually it was not the case, because for all reduced collectives we were able to use NCCL, but for hello exchange peer-to-peer communication we had to resolve back to MPI, which was quite slow compared to NCCL. There's also the case of network congestion, as shown in the case, and this is something that we could not overcome, and that's because for many of the data, we profiled this, and we can see that for some communication, it falls on our ideal line that we expect. However, because of congestion and these kind of things, you can see many samples fall outside of the range that we project. Another limitation is memory capacity, and this is because there's some redundancy in memory for some strategies, because activations are not distributed. I mean, activations are distributed, for example, in case of channel and filter, but the weights are not. And distributing the weights would require some extra overhead, and therefore we stuck to just distributing the activations. There is also the problem of the memory manager, where kernels are launched asynchronously, but they have to wait for memory allocation, and this leads to performance degradation. On computation, there is some significant amount of time spent on weight updates, and this forms a big part of the total compute time. And also in the case of workload balancing, like I mentioned earlier, for pipeline, we have to ensure that we split the model perfectly such that all the parts take more or less the same time. And there's some computational redundancy involved, introduced by the frameworks, and also that the convolutional layers don't scale perfectly as expected. In terms of scaling limitations, we are limited to the number of, for example, in the case of filter and channel, we're limited to the number of channels and filters available. We cannot scale beyond that. And we found that using a hybrid in this case is very good, because it combines we can do the filter or channel in the local and in a single node, and then do a hybrid when we want to do more GPUs. Other observations include the rise of hybrid parallelism, because it offers better alternatives for cases where data is limited, and it's much better in terms of scaling. There's also some significant amount of time spent on staging and I/O overhead, which was out of the focus of this paper, but we still wanted to highlight that. And also an emergence of distributed inference because of these large models. Therefore, we need to when we're doing inference, we need to do them in a distributed fashion. And the things we observed in this paper are also applicable in distributed inference. As a summary, we proposed a model for characterizing and identifying the best technique for CNN distributed training. We ran experiments up to 1,000 GPUs and compared this with our analytical model. And ParaDL can project ideal performance with accuracies of 85%, and it helps identify the bottlenecks and limitations for different parallel strategies. That's about it. Thank you very much. This work is a collaboration between these institutes, and yeah, thank you very much.